Thank you for the introduction. Now I can use 30 minutes. I'm from Norwegian University of Science and Technology, Trondheim. I will talk about nickel as well, not only high-strength steels. Here is the overview of my talk. First, I will give the background of my talk. And I will talk about the HEAP project, which I'm leading in Trondheim, and some of the results. And also, I will summarize the challenges. I'm always proud to present the beautiful pictures of my group members. In my group in Trondheim, we have two professors. Professor Jing, she's chairing another session now. We have two adjunct professors from the industry. We have two postdocs. Currently, we have 18 PhDs. We have several visiting PhDs. We have 3 master students. We have very few master students. And we are contributing 10 presentations to ECF 21. I would also like to give you a short introduction of our background of our research. We have been working on fractal mechanics and the degradation of materials for many, many years. We're still working on these classical topics like modeling ductile fracture, corrective constraints, and residual stress effects, pre-strain effects, mismatch effects, etc. Recently, we have moved to Arctic materials because Arctic technology is very important for Norway. And we are concerned with hydrogen embrittlement, ductile to bridge transition. 1/3 of our research is on the classical topic. 2/3 of our research are on the nanomechanics. I established the NTNE Nanomechanical Lab 10 years ago. Now we have 2/3 of our activities in nanomechanics and nanotechnology. In the beginning of this millennium, there are several major accidents happened in Norway for the offshore pipelines due to hydrogen-induced stress cracking. The scale of these accidents was so huge, such that the industry wanted to start the investigation immediately. So we have started several testing projects. HISC-1, HISC-2, 3, 4, and in the last 11 years, from 2002 to 2013. The aim of the project was to establish practical limits for the use of supermagnetic and duplex stainless steels to be implemented in design procedure through testing. We have tested a lot. And you see the major oil companies were involved. The result of this testing was the design of guidelines proposed by DNV. However, after these testings, we realized that hydrogen embrittlement, the fundamental mechanisms are still not understood. We cannot only testing. So we really have to get some fundamental understanding of the hydrogen embrittlement. And the Research Council heard our crying for fundamental research. So I and my team supplied a proposal to the Research Council of Norway. And we were fortunate to be funded a research project. And the title is Hydrogen-Induced Degradation of Offshore Steels in Aging Infrastructure, Models, Prevention and Prediction. The main purpose was to develop a model framework which couples and describes the hydrogen degradation mechanism at different length scale towards in mechanism-based integrity assessment program. Here are my project teams, and the main focus of this project is ground boundary. You have seen the pictures presented by my student Kai Zhao, and we are doing both experiments and also multi-scale simulations and multi-scale experiments. What's special is that we are going to verify these models at different levels. So we have started from nano, micro to macro, and we have already existing large database. And in addition to the database, we are also doing atomic scale verification and nanoscale verification. 2 years ago, we organized ECF20, and 2 weeks ago, we organized a nice workshop. Some of you may be familiar with this picture. And we got 70 participants from 8 countries, organized this nice workshop on hydrogen embrittlement. So in this HEAP project, we are doing atomic probing on the effect of ground boundary. And here are some examples. So we have started the decohesion mechanism, hydrogen enhanced decohesion mechanism. Put the ground boundary into the between the two crystals, and use DFT calculations to calculate the energy before and after the fracture. Here are some typical results. Some of you may already have seen. Here are the fracture energy, and it seems ground boundary has a strong influence on the fracture energy. Sigma 3, if we look at the circle here, sigma 3 ground boundary has a little effect, but sigma 5 has dramatic effect. This shows that DFT is a very powerful tool to probe the effect of ground boundary. This is nickel. And in addition to the DFT, so we have nanomechanical probing of the ground boundary effect. So Aflus and his students are heavily involved with nanomechanical probing. So we can use EBSD to identify the ground boundary, which is of interest. Then use nanomachining. Let's say use FIB, focused ion beam, to cut the specimen with the intended ground boundary, and use in situ charging, and put this whole specimen into the nanoindentor, and to compare with and without ground boundary, and then use the numerical models to understand the effect of ground boundary. You have seen results from my student Kai Zhao. He has used molecular dynamics to probe the effect of ground boundary. Here maybe it's not so easy to see. Vertically is the KID, the K1 stress intensity factor for dislocation emission, as a function of hydrogen numbers. These hydrogen numbers can be easily converted to the hydrogen concentration. Here we can compare the single crystal and the bicrystal. What he found is that the hydrogen concentration will strongly influence the K1D, and in addition that he has developed a continuum model which can capture the duality of the hydrogen and the ground boundary effect. These are very exciting results, and we're going to refine these results very soon. Finally, I would like to introduce some new results on the hydrogen embrittlement simulation of high-strength steels. now it's quite a common practice to simulate the hydrogen-enhanced decohesion by cohesive zone model. And we know that here vertical axis is the traction, that's the stress, and horizontal is the separation. This is the distance. This traction separation law is influenced by hydrogen. In the beginning, we have virgin material. If you have more hydrogen, this law will be decreased. And we can easily implement this cohesive zone together with hydrogen diffusion into finite element model. The question is, we have been asking ourselves, is it possible to transfer the hydrogen degradation effect from one specimen to another one? We know the hydrogen effect is dependent on the geometry. Hydrogen will have different influence. But the question is it possible to transfer from one specimen to another one? For example, we have hydrogen embollism test results for smooth specimen. Is it possible to transfer to notched one? We have to make a lot of experiments for the notched specimens. So this is a central question. My student, Haiyang Yu, he has presented just another topic. He focused on this work as well. So he used the cohesive zone model to fit all these test results for both smooth specimen, CH without hydrogen, and CH 0.5. These are the global hydrogen. And he fit these experimental results for both notched one and the smooth one. And he plot the critical cohesive zone stress with the local lattice hydrogen. This is the local lattice hydrogen. Here I have to mention that this is the first stage. We have not considered the trapped hydrogen. This is only lattice hydrogen. And we plot these results for different specimen. For the smooth specimen, for the notched radius 0.1, radius 0.8. And it looks disordered. However, if we normalize the cohesive stresses with hydrogen and without hydrogen, we got a very nice fit. And this it's called the uniform hydrogen degradation law. And we have just published this in the beginning of this year. So the critical cohesive stress with hydrogen can be expressed as a function of the critical cohesive stress without hydrogen. And here is a function of local hydrogen concentration. And so what we believe for high strength steels, where lattice hydrogen is dominating, we could probably derive such kind of transferability of hydrogen enhanced degradation effect. So the critical cohesive stress is a function of course, the critical separation distance, which we have been keep this as a constant, and also the eta is stress traxility. And with hydrogen can be expressed as a relation without hydrogen, and move everything into the D, and D is this relation. This is empirical relation. So with this figure, I would like to conclude my talk, or I would like to point some challenges. We have models working at different scales. especially the uniform hydrogen degradation model for high-strength steels, seems promising, of course with limitations. There is a lot of limitations. However, microstructure-informed predictive model, which was the aim of this HIP project, there's still a long way to go. We're still not yet. If anybody has any ideas how to realize these predictive models, I would like to very much to cooperate with you. Thank you very much.
Thank you.